Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to do a couple examples of using the alternating series test to test some series for convergence or divergence. So for part A, we have the sum from n equals 1 to positive infinity of negative 1 to the n minus 1 divided by n. And then for part B, we have the sum from n equals 1 to positive infinity of negative 1 to the n minus 1 times 2n over 3n plus 1. Okay, so let's go ahead and look at part A first. Now, for this series here, we want to test for convergence or divergence, and it is alternating because of this here. Okay, so this is going to alternate the signs, minus, plus, and so on. So, what does the alternating series test actually say? Well, here, if we have a series like this, so in this general form here, negative 1 to the n minus 1 times some pattern b sub n, and if we're summing that from n equals 1 or whatever to infinity, then if the sequence, so here this represents the sequence, if the sequence b sub n is eventually decreasing, in other words, if b sub n plus 1 is less than or equal to b sub n eventually, so what do I mean by eventually? Well, that just means that for the first few, however many finite terms, it's okay if this is not satisfied. All that we need is that eventually for every n past a certain point, we need to have this be true. So past a certain point, we need to have this true all the time. It doesn't have to be true all the time for every value of n ever, just for every value of n beyond a certain point. So if this is not true for n equals, say, like 1 to 100, that's okay. As long as after n equals 100 it is true, then we're okay. So that's what I mean by eventually, is that we don't have to have this true all the time, just eventually after a certain point. Okay, and then so if this is true eventually, and if the limit as n goes to infinity of this b sub n without this is 0, then the series, the entire alternating series, converges. Okay, so let's go ahead and see how we can apply that to the problem that we have for part A. So for part A, first let's go ahead and rewrite the series in this form here so that we can identify our b sub n. So for part A, we have the sum from n equals 1 to positive infinity of negative 1 to the n minus 1 times 1 over n. Okay, so now it's more closely in this form here. So then our b sub n is going to be this 1 over n. Okay, so that's what's happening there. So then our b sub n equals 1 over n. Now, is it true? So we want to verify two things. We need to have this be true eventually, and we need to have this be true. So b sub n plus 1 is less than or equal to b sub n. Is that true? Well, what would that mean? That would mean 1 over n plus 1 is less than or equal to 1 over n. Okay, because if b sub n is 1 over n, then b sub n plus 1 is 1 over n plus 1. Okay? So is this true? And yes, it is true. How could we see that? Well, so just think of it as here, n plus 1 is larger than n. So if you divide by a larger number, you're going to get something smaller. So to make this more clear, we can multiply both sides by n times n plus 1. Or rather, multiply both sides by n times n plus 1. Sorry. So these n's cancel, these n plus 1's cancel, and then this is what we're left with is n is less than or equal to n plus 1. Okay? And because n is always greater than 0, it turns out that this inequality is equivalent to this inequality. In other words, this inequality is equivalent to this inequality, and this inequality is clearly always true. Of course, any number is going to be less than or equal to the number that's 1 larger than it. Okay, so n is always less than or equal to n plus 1. So this is actually true always. So our first condition is satisfied. And then how about the second condition? So we need to also have this true. So now we also want to look at the limit as n goes to positive infinity of b sub n. Well, that's the limit as n goes to positive infinity of 1 over n. And what we have here is n is getting really super huge. 1 just stays 1. So we have 1 divided by super huge numbers. So the end result is just going to be 0. So yes, this is also satisfied. So both of these conditions are satisfied. and therefore by the alternating series test, this does converge. So this series here converges. Okay. So what about the series in part B? Let's go ahead and go to a new page. So let's go ahead and rewrite the series. So we have n equals 1 to positive infinity, negative 1 to the n minus 1, 3n over 4n plus 1. Okay, so what's our b sub n? Well, our b sub n is this guy right here. Okay, that's our b sub n. So b sub n equals 3n over 4n plus 1. Now we want to verify this and this. So let's actually focus on this first. So let's consider the limit as n goes to positive infinity of b sub n. That's the limit as n goes to positive infinity of 3n over 4n plus 1. But notice that this is actually, because we have the highest power of n on top is just n to the first, and the same thing on the bottom, just n to the first, then this limit is going to be this 3 divided by that 4, which is 3/4. And notice that that is not 0. Let's go ahead and make that easier to read. 3/4, and this is not 0. So what we see then is that this is actually not satisfied. Now we have to be very, very careful here. That doesn't automatically mean that the series diverges. Okay, it doesn't automatically mean that. All it tells us is that the alternating series test is not going to help us. Okay, because this here is the alternating series test, and it tells us that if this is satisfied and this is satisfied, then the series converges. It doesn't give us any information at all if one or both of these things is not satisfied. Okay, so it doesn't say, well, if they're not satisfied, then the series diverges. All it says is that if they are satisfied, the series does converge. So we don't know what happens in the case that these are not satisfied. So what we have to do then is look at another test. So what we can try here is the nth term test for divergence. So we'll try the nth term test for divergence. That says divergence. And what that is, so what we want to do is for this entire series here, so let's look at n equals 1 to infinity, negative 1 to the n minus 1, 3n over 4n plus 1. What we want to do is consider this entire thing, okay, the entire term, and we'll call that a sub n. And what we want to do is look at the limit as n goes to plus infinity of a sub n. Now, the nth term test for divergence says if this limit is not 0, then the series diverges, okay? So let's investigate that limit. Well, that's the limit as n goes to positive infinity of negative 1 to the, negative 1 to the n minus 1, 3n over 4n plus 1. Okay, so we have the limit as n goes to infinity of all that. Now, this actually, we have a problem here because as n gets larger and larger, this part right here, this negative 1 to the n minus 1, that keeps bouncing back and forth between 1, negative 1, 1, negative 1, 1, negative 1. So what that means then is that as n shoots off to positive infinity, this entire thing keeps bouncing back and forth between positive, negative, positive, negative, positive, negative. So the limit actually does not exist because this oscillation just does not stop. Okay. And also this 3n over 4n plus 1 contributes to that as well, because as n goes to infinity, as we already know, this goes to 3/4. So essentially the limit, or well, the limit doesn't exist, but essentially the expression just keeps bouncing back and forth between positive and negative values, and because this does not go to 0 by itself, then the entire thing cannot go to 0. So this limit does not exist, dne. And of course, if the limit doesn't exist, then it can't equal 0. So limit as n goes to infinity of a sub n does not equal 0. Therefore, by the test for the nth term test for divergence, this entire series diverges. Okay. So the entire series diverges. And again, I do want to point out that just because the alternating series didn't satisfy this condition here, that didn't automatically mean that it diverges. And in this case, it turns out it did diverge, but that may not always be the case. So if you are using the alternating series test and you find that one or both of these conditions are not satisfied, don't just automatically say, oh, it's divergent. Make sure that you try another test, like we did here. We tried the nth term test for divergence, and we found that, in fact, the series does not converge. Okay, so this has been 2 examples of using the alternating series test and then the nth term test for divergence to test some series for convergence or divergence. So I hope you found this video helpful, and thank you for watching.